welcome to the deep dive. Today we're jumping headfirst into serverless streaming architectures.
Yeah, and we're using a really great document from Amazon Web Services as our guide here.
Right. The idea is forget the headache of managing servers. We're looking at processing modern data, focusing on the insights.
Exactly. And stream processing is just getting bigger and bigger, right? Doing it serverlessly is, well, becoming key.
Definitely a superpower in this data world.
So this AWS doc, it lays out 3 core patterns for serverless stream processing.
And that's our mission today, right? To unpack these patterns.
Yep. See how they work in the real world, look at best practices, and, even touch on the costs involved.
Okay, let's unpack this. Serverless computing first. What's the elevator pitch?
Think of it like you build and run your apps without thinking about servers at all. You focus purely on your code, your business logic.
Like renting a kitchen only when you cook and someone else cleans up.
Kind of, yeah.
Yeah.
And AWS Lambda is a big player here, like the doc highlights.
All right, the compute service. It just runs your code when an event happens.
Exactly. Triggered by events, and the billing is pay-per-use. Only pay when it's actually running.
Pretty slick.
And that fits perfectly with streaming data.
Okay, define streaming data for us.
It's data that's generated continuously. Think of it like a river, not a lake. High volume, often small chunks of data.
And you need to process it fast.
Yeah, real-time or near real-time. Much quicker insights than old-school batch processing, where you wait.
So examples would be like .app, log files.
Log files, yeah. E-commerce purchases happening right now, social media feeds.
.iot sensor data, all that constant chatter.
Precisely. So our goal, our deep dive mission, understand these 3 patterns.
See them in action. I think the doc uses a medical sensor use case.
It does, yeah, a really good one. We'll look at best practices, cost stuff.
All right, let's plunge in. Pattern 1, sensor data collection with simple transformation.
Okay, so the basic idea here, you've got IoT sensors, maybe on machines or devices.
Constantly sending measurements.
Right, some ingest service. And as the data comes in, it gets simple tweaks just to get it ready for later.
And the medical sensor example, how does that fit?
It's a great example. You have medical devices tracking patient data, but you've got HIPAA compliance, right?
The privacy rules. You need to handle sensitive info carefully.
Exactly. Things like patient name, date of birth, that's PII, personally identifiable information. It needs to be removed.
So that removal, that's the simple transformation, de-identification.
That's it, de-identification.
Okay, walk us through the flow. How does the data travel?
So picture these medical devices on a patient sending data. They might use something lightweight like MQTT.
Like a way for devices to whisper data.
Yeah, basically. Sending it to an AWS IoT gateway. The raw record, the doc shows, has like timestamp, device ID, patient ID, name, date of birth, and the readings.
All the sensitive stuff included initially. What happens next?
Well, the IoT gateway is smart. You can set up rules, so a rule gets triggered when data arrives.
And that rule triggers.
A Lambda function automatically.
Yeah. Okay, and this Lambda is the de-identifier.
Correct. It takes that record, pulls out the name and date of birth.
Gone. But how do you track which patient is which later, if you need to?
Good question. The function stores a mapping the link between the now anonymized patient ID and the info it removed in a DynamoDB table.
DynamoDB, the NoSQL database.
Right. And crucially, that stored PII is encrypted. It uses AWS KMS, Key Management Service.
Like a digital vault for the encryption keys.
Yeah.
Managed by AWS. Secure.
Very secure. So after Lambda's done its work, you have a clean record.
No name, no date of birth, but still timestamp, device ID, patient ID, medical readings.
Exactly. And this cleaned up, de-identified data gets sent to a Kinesis data firehose delivery stream.
Kinesis data firehose. What's its job?
Think of it as a super efficient delivery pipeline for streaming data. It reliably gets high volume data into data lakes like S3, databases, analytics tools.
And it manages the infrastructure behind the scenes.
Totally. You don't worry about scaling the delivery part.
Okay, the flow makes sense. What about best practices? How do you build this well?
The document has some great tips. First one, separate your core Lambda logic from the handler.
The handler being the bit AWS calls.
Yeah. Put your actual de-identification code in its own module or class. Makes it way easier to test independently.
Unit testing your core logic without needing the whole AWS setup. Smart.
It's just good software design, really. Separation of concerns. Makes things more robust.
Makes sense.
Yeah.
What else? Something about container reuse.
Right, Lambda container reuse. This is for performance.
How does that work?
So when Lambda runs your function, it often reuses the underlying execution environment, the container for the next invocation, if one comes quickly.
Like a warm start.
Exactly. Things you initialize outside your main function handler, like database connections, loading configurations, dependencies that can persist between invocations.
So subsequent runs are faster because they don't need to set everything up again.
Precisely. You cache configurations, use static initialization where possible. It makes a difference.
Cool, like having your tools ready. Any other tips for this pattern?
Yeah, regarding Kinesis Data Firehose sending data to S3, you need to tune the buffering.
Buffering, like how much data it collects before sending.
Right. Firehose buffers data based on size or time interval before delivering it as an object to S3.
And why does tuning matter?
Well, if you set the buffer too small or the interval too short, you end up with loads and loads of tiny little files in S3.
Okay. And that's bad because...
It can get expensive. There are costs associated with each S3 PUT request, and managing millions of tiny files is also less efficient for later processing.
So you want to find that sweet spot. Reasonably sized files, not a million tiny ones.
Exactly. Optimize for S3 object size and related to cost.compression.
Use GZIP or Snappy or something.
Yeah, GZIP, Snappy, Zip.
Yeah.
Compressing the data before Firehose writes it to S3 saves on storage costs and potentially data transfer costs too. Smaller files, less cost.
Makes perfect sense. Okay, the bottom line, cost. What are the estimates?
The document gives some rough monthly figures. Small scale, maybe around $117.
Okay.
Medium scale jumps up to about $1,132.
Wow, quite a leap.
And large scale, you're looking at nearly $5,000 a month, around $400 and $978.
Those are big ranges. What drives the difference mainly? Data volume.
Mostly data volume, yeah, and processing frequency. The document appendix has detailed breakdowns showing which service costs what. Worth checking if you're planning this.
Definitely. Good to know where the money goes. Okay, ready for pattern 2.
Let's do it. Pattern 2, Stream Ingest Transform Load, or ITL.
ITL. Okay, sounds like we're adding more steps. How does this build on the first pattern?
It takes that initial de-identified data and adds enrichment, pulling in extra context from other datasets.
Enrichment, like adding more info to the record.
Exactly. Usually from relatively small, fairly static datasets. Think of it as adding useful labels or details.
So back to the medical sensors. What kind of enrichment would make sense there?
The doc suggests adding device details, like based on the device side, look up the manufacturer and the specific model of that sensor.
Okay, so you know what kind of device generated the reading.
Right. Or another common one is enriching web logs with geolocation data based on an IP address.
Gotcha. So how does this fit into the flow? We have de-identified data coming from the first Firehose stream.
So that stream becomes the input for another Firehose delivery stream.
A second Firehose.
Yep. And the second one is configured to invoke a different Lambda function.
A dedicated enrichment lambda.
Exactly. Its only job is to add that extra context.
And where does it get the context? Like the manufacturer info.
It would look it up, probably using the device blob from the record to query a DynamoDB table that holds that device metadata.
A quick lookup in DynamoDB.
Right. Grab the manufacturer, grab the model.
And add them as new fields to the record.
Precisely. So now your record has the original de-identified data plus manufacturer and model.
And then this enriched record.
Gets delivered by that second Firehose stream to its final destination. Could be S3 again, maybe a data warehouse like Amazon Redshift.
Okay. And the doc mentioned something about a backup copy.
Yeah, smartly, it suggests also saving a copy of the raw, just de-identified records from the first Firehose stream directly to S3 as well.
Why do that?
It's a safety net. If something goes wrong with your enrichment logic later, you still have the original, untransformed but de-identified data safe in S3.
Insurance. I like it. Now, serverless scaling. How does Lambda handle this enrichment step if data volume spikes?
This is where it really shines. Again, Lambda just automatically scales out. More data comes in. AWS spins up more instances of your enrichment Lambda function to run in parallel.
So it handles bursts automatically.
Totally. And scales back down when traffic slows.
Yeah.
You don't pay for idle enrichment capacity.
That's huge compared to provisioning servers for peak load.
Massive difference. It lets you focus on the enrichment logic, not capacity planning.
What about best practices specific to this ITL pattern? Anything new?
A few things. If Redshift is your destination, you definitely want to look into Redshift's own best practices for data loading. Copy by command options, distribution keys, sort keys, that kind of stuff.
Right. Optimize for the target system.
Yeah. And related to that backup point we just discussed,
The insurance copy.
yes, Firehose has a feature called Source Record Backup. The document strongly recommends enabling this when you use Lambda for transformation.
Why specifically?
If your Lambda function throws an error and fails to process a batch of records, Firehose can automatically put those original untransformed source records into a separate S3 location.
Ah, so you don't lose data even if your code has a bug. That's crucial.
Absolutely crucial for data integrity. Another point is balancing Firehose buffer size against Lambda limits.
We talked about buffer size for S3 files. How does it affect Lambda?
Well, larger buffers mean fewer Lambda invocations, which can save cost, but Lambda functions have a maximum execution time limit, currently 15 minutes, though it used to be 5 minutes, as mentioned in older docs, so always check current limits.
Okay.
If your enrichment logic takes a while per record, and you have a really large buffer size, meaning many records per invocation, you could potentially hit that timeout.
So too big a batch might time out the function. It's a trade-off.
That's a balancing act, cost versus processing time per invocation. And one more tip.
Yes.
If those lookups to DynamoDB for enrichment data become a bottleneck, especially at high volume, consider DynamoDB Accelerator, or DAX.
DAX. What's that?
It's an in-memory cache specifically for DynamoDB. Sits in front of your table.
So it makes lookups faster.
Dramatically faster for frequently accessed items,
Yeah.
reduces latency, increases throughput. It can even lower the load on your DynamoDB table itself.
Caching the common lookups.
Yeah.
Okay. Cost for pattern 2. You said pattern 1 could get pricey.
Right. Interestingly, for ITL, the estimates are lower, especially at the small scale. Small's around $18 a month.
$18. Down from $117. That's way cheaper.
Yeah. Medium is about $138, and large is around $672.
Still cheaper than pattern 1 across the board. Why would adding a step potentially be cheaper?
It's likely due to how the processing is structured, maybe more efficient batching in the second Firehose, potentially different Lambda configurations. The appendix at Punt2 has the details.
Fascinating. Shows careful architecture design really matters for cost. Okay, on to the grand finale. Pattern 3. Real-time analytics.
Right. Now, we're not just prepping the data, we're actively analyzing it as it streams.
What kind of analysis are we talking about?
This pattern adds things like windowed aggregations, calculating averages, sums, counts over specific time periods, and importantly, anomaly detection, finding weird stuff in the data flow.
How does that apply back to our medical devices?
The use case in the doc is about detecting anomalies in measurements across all devices from a certain manufacturer.
Why would you do that?
Think proactive maintenance. If you see weird readings starting to pop up across multiple devices of the same model, maybe there's an issue brewing. You can flag it before devices actually fail.
Ah, predictive maintenance based on real-time data. Huge value there.
Huge, and generating alerts for critical situations, obviously.
Who benefits from this?
Well, the hospital using the devices less downtime, potentially better patient care. And the device manufacturer, they can offer better service contracts, spot design issues faster.
Win-win. So data flow. How does this layer on top?
Okay, so the enriched data from Pattern 2 now flows into Kinesis Data Analytics.
Kinesis Data Analytics. What does that do?
It lets you run standard SQL queries directly on the streaming data, real-time SQL.
SQL on streams. That's powerful. What kind of query for the anomaly detection?
The doc shows an example using a built-in function called random cut forest.
Random cut forest. Sounds fancy.
It's an algorithm specifically designed for anomaly detection on streaming data. The SQL query uses it to calculate an anomaly score for each incoming record.
Okay, so each record gets a score indicating how unusual it is.
Exactly. High score means more anomalous.
What happens with these scores?
They are sent out from Kinesis Data Analytics to another Kinesis data stream.
Yet another Kinesis stream.
Yep, and listening to this stream is another Lambda function.
Okay, what's this Lambda doing?
It processes the anomaly scores. It checks if a score is above a certain threshold you define.
A threshold for too weird.
Pretty much. If a score crosses the threshold, the Lambda function triggers an alert. Maybe sends an SMS via Amazon SNS, simple notification service.
So high score, BAS, Lambda, SNS, alert. Real-time notification.
That's the flow. And the doc mentions you can set that threshold and the SNS topic easily using Lambda environment variables. Very configurable.
Nice. What about the original enriched data? Is it still saved somewhere?
Oh, yeah. That continues to be delivered to S3, just like in Pattern 2. So you still have the full enriched history for later, deeper analysis or model training.
Good. You always want that raw material. Best practices for this real-time analytics layer. especially with Kinesis data analytics.
A few key ones. First, schema discovery. Kinesis Analytics tries to figure out your data structure automatically.
By sampling the input stream.
Right. But if your stream has lots of different record types, it might miss some or create a schema that doesn't quite fit everything.
So you might need to define the schema explicitly.
You might, yeah. Or at least carefully review the auto-discovered one, especially with diverse data sources.
Makes sense. What else?
Definitely set up at least 2 outputs for your Kinesis Analytics application.
2? What for?
One for your main query results, the anomaly scores in our case. The second should be an error stream.
An error stream.
Yeah. Any records that the application fails to process due to errors in your SQL or data format issues, they get sent to the separate stream. Usually you'd pipe this error stream to S3 using Firehose.
Ah, so you can easily find and debug processing errors without disrupting the main results flow. Very smart.
Invaluable for troubleshooting. Also, some tips for writing the Kinesis Analytics SQL itself.
Why, yeah.
When developing, use small window sizes in your queries. Lets you see results faster and iterate quickly.
Good tip. Faster feedback loop.
Break down complex logic. Use intermediate in-application streams to store results from one step and feed them into the next. Easier to debug than one giant query.
Modular SQL, essentially.
Kind of, yeah. And for time windows, like tumbling windows, consider using both processing time, when analytics got the record, and event time, the timestamp in the record, if possible, helps handle data arriving out of order or with delays.
Right, makes the time analysis more robust. Okay, final cost check. Pattern 3, real-time analytics.
The estimates here are small scale, around $706 per month.
Okay, up from the ITL pattern.
Medium scale is about $817.
Not a huge jump from small to medium there.
And large scale is around $1,312.
Interesting. The scaling seems less dramatic here than in pattern 1. Why might that be?
Yeah, it's a different cost profile. The main drivers are the Kinesis Data Analytics Processing Units, KPUs needed to run your SQL, the Kinesis Data Streams throughput, the alerting Lambda invocations, and S3 storage. Appendix 8.3 breaks it down. KPU costs might dominate more than pure data volume costs at certain scales.
Got it. So we've seen these 3 powerful patterns. Does the document mention companies actually using this stuff in the wild?
Oh yeah, definitely. It highlights a few great customer case studies. Thomson Reuters. They process something like 25 billion events a month for product insights.
Billion.
Yep. Using Lambda, Kinesis streams, Firehose, analyzing user interactions to improve their products constantly.
That's massive scale. Anyone else?
iRobot, the Roomba folks. Their whole connected vacuum platform runs on a serverless architecture.
Completely serverless.
Apparently so. Using Lambda, AWS IoT platform, Kinesis, and the kicker, they manage it all with a pretty small team. Shows the operational leverage you get.
Wow. Less infrastructure management, more focus on robot features. Makes sense. One more.
Nextdoor. The neighborhood social network. They built a serverless ETL pipeline on Lambda.
ETL extract, transform, load.
Right. Handling 2.5 billion syslog and tracking events daily. They moved from a traditional system because managing it was becoming a huge drain.
So serverless freed up their engineers to focus on the actual Nextdoor product, not data pipelines.
Exactly. These examples really show it's not just theoretical. Companies are getting real value.
Absolutely. So, wrapping up this deep dive, what are the big takeaways, the core advantages of this serverless streaming approach?
I mean, number one, no server management. Huge win.
Definitely.
Then you've got the flexible automatic scaling, handles peaks and valleys without you doing anything.
Built-in high availability, fault tolerance.
Yep. And that pay-per-use model. You only pay for what you actually compute or process. No paying for idle servers.
And we saw how moving towards real-time analytics gives you those faster, deeper insights.
For sure. Combining serverless agility with stream processing power lets you build these complex apps faster.
And organizations pay for value, not just infrastructure.
That's the promise.
Yep.
Focus on the data insights.
So a final thought for everyone listening. How could these patterns change things for you in your field with your data challenges?
Yeah, could shifting away from managing infrastructure towards just extracting value from data in real time, could that be a game changer for you?
Something to think about. We definitely encourage you to explore AWS serverless services more and check out the source document we discussed for all the nitty-gritty details. It might just spark some ideas for your own projects.